Until measured, each particle exists in a superposition of possible states. 3. The moment you measure one particle, the other immediately takes on a corresponding state, even if it's on the other side of the universe. This defies our normal understanding of cause and effect. If no signal can travel faster than that, how does the second particle know what the first one's result was? Einstein believed this meant quantum mechanics was incomplete. He suggested there might be hidden variables, unknown factors that already determined the outcome before measurement. But in the 1960s, John Bell developed a test to prove whether hidden variables existed. Experiments confirmed that entanglement is real, and no hidden variables explain it. This paradox forces us to question the nature of reality. Is information traveling instantly, breaking the speed of light? Does measuring one particle somehow affect the past? Is reality fundamentally connected in ways we don't yet understand? One possible explanation is the idea that space itself might not be what we think. It could be that entangled particles are not truly separate, but exist as part of a deeper, hidden connection beyond three-dimensional space. The quantum entanglement paradox makes us ask, if two particles can be instantly linked across the universe, what does that say about the fundamental nature of reality? Welcome to level 64 of 100 paradoxes. Imagine a universe where everything that has ever happened will eventually happen again. Every moment, every thought, every event, repeating over an unimaginably long time scale. This is the strange implication of Poincare recurrence theorem, a concept that challenges how we think about time, randomness, and the fate of the universe. Proposed by mathematician Henri Poincaré, the theorem states that in a finite system with fixed energy, given enough time, the system must eventually return to a state arbitrarily close to its original condition. To understand why, imagine a box filled with gas molecules bouncing around randomly. Over time, the molecules will explore every possible arrangement within the box. Since there are only a finite number of ways they can be arranged, eventually, by pure chance, they must return to a previous configuration, no matter how unlikely it seems. This idea applies not just to gas molecules, but to entire universes. If our universe is a finite system that follows deterministic laws, then over a long enough time scale, everything, every galaxy, every planet, even every thought you've ever had, will happen again. The paradox is that, in practice, this time scale is incomprehensibly huge. For a system as large as the universe, a full recurrence could take trillions upon trillions of years, far longer than the current age of the universe. This leads to deep philosophical questions. Does this mean time is an infinite loop? If everything repeats, do we have free will, or is reality just playing a repeat? Could this be the explanation for déjà vu, echoes of past recurrences? Some scientists argue that the Poincare recurrence theorem doesn't apply to our universe because of entropy, the fact that disorder always increases. But if the universe is truly a closed system, then recurrence is not just possible, it's inevitable. The Poincare recurrence theorem forces us to ask, is the universe heading toward an infinite cycle of rebirths where everything we experience has already happened countless times before? Welcome to level 65 of 100 paradoxes. Imagine stepping into a futuristic teleportation machine. It scans your entire body, down to every atom, and transmits this data across space. On the other side, a perfect copy of you is reassembled. Same thoughts, same memories, same consciousness. But here's the question. Is that still you? This is the teletransportation paradox, a thought experiment that challenges the nature of identity, consciousness, and what it means to be you. The paradox works like this. You step into the teleportation machine. The machine scans and destroys your original body to avoid duplicates. The exact information is transmitted elsewhere and used to create a perfect replica of you. The new version of you steps out, remembering everything as if nothing happened. From an outside perspective, teleportation worked. Your body disappeared in one place and appeared in another. But if the original version was destroyed, what happened to your consciousness? Some argue that since the copy is perfect, your experience continues seamlessly, meaning teleportation is just a high-tech way of moving. Others argue that the original you ceases to exist, meaning every teleportation is actually a form of death, replacing you with a duplicate who only thinks they are you. This paradox raises unsettling questions. Is personal identity tied to physical continuity, or just to memories and patterns? If teleportation kills the original, is every copy a new person who only thinks they are the same? If consciousness is just information, could multiple copies of you exist at the same time? The teletransportation paradox forces us to ask, are we more than just the sum of our memories and atoms? And if a perfect copy of you exists, is there any meaningful difference between the original and the duplicate? Welcome to level 66 of 100 paradoxes. Imagine taking a solid sphere, like a basketball, and breaking it into a few pieces. Now, without stretching, shrinking, or adding anything, you rearrange those pieces, and suddenly you have two identical basketballs. This is the Banach-Tarski paradox, a mind-blowing mathematical result that seems impossible. It states that in the world of pure math, it is possible to take one object, split it into a finite number of pieces, and reassemble them into two objects the same size as the original. Here's how it works. In everyday life, cutting something in half means each piece is half as big. But in higher level mathematics, objects aren't just made of small parts, they are made of infinitely many points. The paradox takes advantage of this by dividing an object into non-measurable sets, collections of points so complex that they don't behave the way normal shapes do. The proof, developed by Stefan Banach and Alfred Tarski, relies on advanced set theory and the axiom of choice, a controversial rule in mathematics that allows for picking elements from infinite sets in ways that seem unintuitive. But before trying this on your basketball at home, here's the catch. This paradox only works in pure mathematics. In the real world, physical objects are made of atoms, and you can't separate them into infinitely complex sets. It challenges our basic ideas of size and volume. In normal geometry, when you cut an object, the total volume stays the same. But the Banach-Tarski paradox suggests that, mathematically, volume can't be doubled. It suggests that infinity doesn't follow normal logic. If space itself were infinitely divisible in reality, could something like this actually happen on a cosmic scale? The Banach-Tarski paradox forces us to ask, if mathematical logic allows objects to duplicate, does that mean our understanding of space and matter is incomplete? And if infinity plays by different rules, what else might be possible in the world of pure mathematics?
Stop stressing over this. Mighty Patch pimple patches reveal clear-looking skin overnight. Pimple, meet your Mighty Patch.
Yeah, getting too cool. Show them Temptation's Tinder fills.
Who are you texting? I'm shopping for a car on the A car?
Are you sure you can afford it? That's a big purchase.
Relax. I got requalified and shopped by my monthly budget, so I know it's a good decision. Unlike Jenny's new piercing.
Since 1875, together as one, we are possessed by an attainable desire to seek beyond the ordinary.
Do you want to be driven? Do you want to be dedicated to something? Do you want to be pushed? Do you want to achieve more? Do you want to excel? Are those things that you're looking for? Well, come to Success Academy.
Welcome to level 67 of 100 paradoxes. Imagine trying to walk across a room. Before you reach the other side, you must first get halfway there. Then, before you can reach the end, you must travel half of the remaining distance. Then, half of that, and so on, forever. This is Zeno's dichotomy paradox, a problem that suggests motion should be impossible. The logic is simple. To move from point A to point B, you must first get halfway. But before you reach that halfway point, you must first get halfway to halfway. No matter how close you get, there will always be another halfway point left to reach. Since there are infinite halfway points, it seems like you will never actually reach your destination. But in real life, people walk across rooms, arrows hit targets, and motion happens all the time. So, what went wrong? The paradox happens because it assumes that adding up an infinite number of steps must take an infinite amount of time. But in reality, The sum of all these steps can still be finite. For example, if you keep cutting the distance in half, the total distance adds up to 1. Even though there are infinite terms in the sequence, their sum still converges to a finite number, meaning motion is possible. This was formally solved using calculus, developed centuries later by Newton and Leibniz. Their work showed that an infinite series can have a finite sum, resolving Zeno's paradox mathematically. But the deeper question remains. If motion is continuous, does space itself break down into smaller and smaller parts forever? Is there a fundamental limit to how small distances can get? Or is the universe truly infinite in its divisibility? Does time itself flow smoothly, or does it jump in tiny increments like frames in a movie? Welcome to level 68 of 100 paradoxes. Imagine trying to measure a tiny particle, like an electron. You want to know exactly where it is and how fast it's moving. But no matter how precise your instruments are, the more you pin down one, the more uncertain the other becomes. This is Heisenberg's uncertainty principle, one of the strangest and most fundamental ideas in quantum mechanics. In classical physics, we expect to be able to measure anything with unlimited precision. If you track a moving car, you can measure both its speed and its location at the same time. But at the quantum level, this isn't possible. The uncertainty principle states that the more precisely you measure a particle's position, the less precisely you can measure its momentum, which is mass times velocity, and vice versa. The paradox is that this isn't just a problem with our measuring tools, it's a fundamental limit of nature itself. Here's why. 1. At the quantum level, particles behave like waves and particles at the same time. 2. A wave is spread out, meaning it doesn't have a single, precise position. 3. The more we force a particle to have a definite position, the more its wave properties get distorted, making its momentum highly uncertain. 4. Likewise, if we precisely measure momentum, the particle's location becomes spread out and uncertain. This means that reality isn't as clear-cut as we once thought. At the smallest scales, particles don't have exact motions and speeds until they are measured. They exist in a fuzzy, probabilistic state. This principle has massive implications. 1. It proves that absolute determinism is impossible. There is no way to predict the exact outcome of a quantum event. 2. It sets a limit on what can ever be known. Some things in nature are fundamentally unknowable, no matter how advanced science becomes. 3. It plays a role in everything from quantum computing to black holes. Even the energy of empty space fluctuates due to uncertainty. The uncertainty principle forces us to ask, if the universe itself is uncertain at the smallest level, how much of reality is truly predictable? And if reality depends on measurement, does that mean the act of observing changes the world around us? Welcome to level 69 of 100 paradoxes. Imagine an infinite hotel, a place with an unlimited number of rooms, all numbers.
So you still have nighttime work.
3, 4, and so on. Every room is occupied, but somehow the hotel can still accommodate new guests. This is Hilbert's
And you
infinite
said
hotel
that
paradox,
doesn't have to
but
do for it.
let's add a twist. What happens if half the
They
guests
should have one more refill.
normally in a
And
finite
they told me
hotel,
I
if
first
half the
getting
guests
into
leave,
and
half
before I
the
leave
rooms
there's
will
like
be empty.
one more.
But
Oh,
in
yeah,
an infinite
one more.
hotel,
Does it
something strange happens.
say?
Suppose
Does it
every
tell you
guest
it has
has
a
an odd
refill?
number of room leaves. So guests in rooms 1, 3, 5, 7, etc. are gone. 2. That means only guests in even numbered rooms remain. Rooms 2, 4, 6, 8, and so on. 3. Now, the hotel manager shifts each guest to a new room by dividing their old room number by 2.
Oh,
Four, the guest in room 2 moves to room 1. The
this
guest
isn't
in
the right
room
one,
4 moves
but
to room 2, and so on. After this simple shift, the hotel is once again completely
I
full,
mean,
even though an infinite number of guests
not
left.
it sounds like it looks like it says a whole lot of Snow White,
Hotel loses
but
half its
honestly,
guests, but still
it says
remains
refill
full.
one.
The number
so
of guests should have gone
I'm like, I don't know
but
if this
in
is
a way,
the second
it
refill
hasn't.
or if
Infinity
this thing has
behaves
one more
in a way
refill left.
that defies normal logic. You can
So
take
it's not
one
necessarily
number of
clear.
things
And that's the
still
daytime
find
one?
infinite
No, that's the nighttime one.
This
But
paradox
they were both
isn't
bought
just a weird
simultaneously.
thought experiment.
You buy like
What's the daytime one?
Truths
I don't know
from
if they bought
mathematics, set theory.
I just have two of the
infinity
nights
itself.
about
It forces us to ask,
So I think because I just took the trash out, so I think I was like cleaning up, and I just kind of like threw it in the
Does
trash.
this mean infinite
And then I
quantities
took
are
the
of the same
recycling
size?
out.
Or are
And I
there
was
different
just like,
kinds of infinity?
why do I need it
If
now?
space itself
No, I
were
was
infinite,
thinking about it
could it
earlier.
work
I
like
know I thought
Hilbert's
to leave
hotel?
it.
The
But I'm like,
infinite
why did I
hotel
leave it like
paradox
that?
with a twist shows us that
That's hot.
infinity doesn't follow
Like
the
that
rules of everyday
That's
numbers.
still in the back. I was like, what is this? I'm not saying.
Welcome to level 70 of 100
It's really solid.
paradoxes. Now,
I'm not
let's dive into a paradox from the
This
strange
one's
world
hard.
of quantum mechanics,
I
the
love
quantum Zeno effect. Imagine you have a radioactive atom that is
Yeah,
supposed to
yeah.
decay
Well,
over
they
time.
should have it.
Normally, it has a predictable half-life, meaning that
They
over a
might
given
have
period,
it.
there's a certain probability that it will decay. But what if you keep measuring it constantly?
That
Quantum
was my
mechanics
biggest
tells
thing,
us
but I was
something
just like,
shocking. The more
if
you
you
observe
can-
the system,
I mean,
the
honestly,
less
I was
it
like, I
changes.
could walk over it.
If you repeatedly
but I
measure
can
an unstable
solve it.
particle, you can actually freeze it in
I
its
just
original
actually
state.
going to
Instead of
or I
decaying
think
as
about asking
expected,
about it.
it behaves as if it is stuck in time.
I'll go.
The
I'm
more
not going
frequently
to
you check, the longer it takes to decay. This is known as the quantum Zeno effect, named
I
after
do
Zeno of Elea,
need
the ancient Greek philosopher famous for his paradoxes of motion. Just like Zeno's paradoxes suggested that motion might be an illusion, the quantum Zeno effect suggests that change itself can be stopped just by the act of observation. But how does this work?
Like, I would have
Comes
just
down to the
attempted to with
fundamental
this
principle
security
of quantum
the
mechanics,
insurance card,
the way
but
of function.
I was just sitting here like,
Before measurement, the
no,
quantum system
I don't
exists
think
in
that's super how
superposition
that
of
works.
multiple
But
states.
but
But
I was like, when I
when
get
you
there,
measure
it's tell me
the wave
it's
function
$6
collapses
for the
into a
insurance.
single
I was like,
definite state.
wow. And
Now, if you keep measuring the system
So,
rapidly, you are
I
constantly
just been,
forcing the wave function to collapse
like, the entire
or
I don't know.
evolve to a new
Wow.
state. As a result, the system remains frozen in its initial condition, preventing it from changing. This effect has been experimentally confirmed in physics labs. Scientists have been able to slow down or even completely halt atomic decay simply by increasing the rate of measurement. Welcome to level 71 of 100 paradox. Imagine uploading your mind into a computer, a perfect digital copy of your consciousness, complete with your thoughts,
I was saying,
memories, and
I was
personality.
honestly saying, like,
The
yeah, you can
original
really see it,
is
you
still
can really
alive,
read.
But now
Like,
a
you'll
second
always be
version
as
exists
intelligent
in
as the
simulation.
internet, but as
Now,
intelligent
here's
as
the
you
paradox.
yourself as a character.
Which one is the
How to
real?
get how to say.
At first, the answer
Like,
seems
also,
obvious. The original
like,
is real, and the copy is just data.
And I
But the
just felt
copy
it's
thinks
like,
exactly
I
like
just think that the
remembers your
universe
entire
like,
life
old
and
things,
believes it is the
something
same
that
person.
scroll down,
Now,
and
let's go
it's-
further.
it's-
What if, after the upload, the original version of you
I
dies?
just think too many people
Does your
are just
consciousness
like, oh, like, I
continue
see
to
what it's
copy,
doing and try to fight
or
against it.
was you lost forever?
Putting you back
Now,
more
Imagine the
on-
process is reversed.
and then you
The
have people
digital
that are
copy
like,
is
oh, well,
downloaded back into a
I'm
new
gonna be like yelling
biological
and
body,
loud.
identical to your original self.
You can't really find
Is this
it.
new version still you, or
It's
has
just
a new
like,
person
it's
been
like,
created?
yeah,
This
well,
paradox exposes a major problem with identity and continuity. Are you just a pattern of information,
we were
or
honestly
is your
like,
consciousness
big
tied to a specific
and, like,
physical
we were just
body?
like, you know what?
If a perfect
alright.
copy of you can exist,
I'm a
does that
witch.
mean you are
My
no longer
abilities is
you?
both.
If
And if I
consciousness
tell
can be
everybody
duplicated,
that,
does it
like,
prove
I
that
don't
the
know
idea of
feelings
self is an
book
illusion?
that's like
One
both.
possibility is that
Everybody's
identity is
not
just an
gonna know
illusion of
you're
continuity.
I.
You feel like the same person from moment to moment,
You're me.
but there is no single continuous
I'm
you.
only gonna have to tell
Instead,
you
you are
know,
just a
you're
process
me,
running on a
but just
biological
get
machine.
it.
And if that process can run elsewhere, you still
But it would
exist.
just end up being
Another
like, really
perspective
right
is that
behind
only the
you.
original experiences
I don't know.
true
It'd be like,
consciousness
just
and a
shooting
copy, no matter
So,
how perfect, is
and
nothing
it's
more
just
than a
like,
simulation.
Some people just don't know they
Welcome to
can
level
do it,
72
but not
of
having to do
100
their own have to go
paradox.
backwards. Like,
A man writes
Ow,
a simple
I
sentence on a piece
need
of paper.
help, and it's
This
just like, you know,
sentence
I must
is
be helpful.
false. 4
Like,
2
I
plus
honestly
2
see you
equals
just
5.
So it's just like,
At first
like
glance,
quite
it
a
seems
simple
like
guy.
just another version of the liar
but everybody's got to do it in the
where a sentence declares itself
And
false.
so you can't even tell the person that really paying attention or not. You get like
But this
somebody else,
one is
and then
different.
it's just like, oh,
It
no,
adds an
we
extra
understand.
condition
They
that makes
just,
the
they
paradox
just started
even worse.
like
If the sentence is
does not
true,
fail
then
monkey
what
out.
it says must be correct.
Like one
This sentence is false, or
It's like
2
I know
plus
he's
2
doing it,
equals
but
5.
obviously trying to.
But since 2 plus 2 does not
It's
equal
just like
5,
that type of thing.
the
right?
first
So,
part must be
so
true.
you tell me
Meaning, this sentence is false, must be true. But that's a contradiction. If the sentence is false, then this sentence is false, should be false. But that would make the whole sentence true, because the second part, or 2 plus 2 equals 5, is still false. No matter how you look at it, the logic collapses into an infinite loop.
That is
Unlike
not
the
that mean.
original liar paradox, where one
That's
sentence
why the
refers
words
to
they get
itself,
separated.
this version introduces an
like
unrelated
people
method to the fact,
like they
making
get
it harder to
like
dismiss
Trump.
as a simple
They're like super good, but
self-referential trait.
obviously sound.
This paradox, known as the liar's revenge,
It's like, this
raises
is what I want to know.
disturbing
Like,
questions.
they're sharing a really
Can
powerful
truth and
position. This is what I
falsehood
want to
exist
know.
in a single statement at the same time?
Take your time.
Does this mean some
What I want to
statements
know, like,
cannot be classified as either true or false?
okay, so
If
this
logic
is what I want to
itself
know.
is a paradox, does
It's
that
just like
mean
that,
it has
like,
limits? Some philosophers and logicians argue that statements like this reveal fundamental gaps in our understanding of truth, suggesting that reality may not be as black and white as we assume. Others believe paradoxes like these show the need for a new system of logic that allows for statements that are neither true nor false, but something in between. The liar's revenge forces us to ask, if contradictions like this can exist,
like
how
character
much of
classes,
what
like
we
acting
assume
and
to be
stuff like that.
logical
Those are so
truth
important.
is actually
Cause it's
fake?
just like I
And if
usually
truth
pick
itself
like
can be
poison out. I
paradoxical,
pick out poison.
what does that
and
mean
like
for everything
you
we
can't
believe
do it
to
in
be
real
real?
life, but yet you try to be a chemistry of class.
Welcome to level
You try to do it on a
73 of
molecular level,
100
but you can't even
paradoxes.
read whether or not
Imagine you're
somebody's
playing a
speaking out
game where the
poison
goal
or
is
like,
simple.
like
Follow
just
the
by like
rules
them
and
not
make a
doing
move
it,
until
by
the
them
game
doing
ends.
it.
Most games, like chess or tic-tac-toe, are
It's like,
finite, meaning they always reach a conclusion. But now, let's define a new game called Hypergame. On your turn, you can either choose to end the game or pick any well-defined game to play. If you choose a game, the players must finish it before returning to Hypergame, where the next player makes their choice. At first, this seems completely new, but here's where the paradox appears. If Hypergame is a well-defined game, then you must be able to pick any well-defined game, including Hypergame itself. Now, the game never truly ends. The first player picks Hypergame again. The next player also picks Hypergame. This can continue forever, meaning Hypergame is an infinite game. But this is a contradiction, because by definition, Hypergame was supposed to be a well-defined game, meaning it should always end. Instead, it creates a paradox by allowing itself to be picked, forming an infinite loop that never resolves. This paradox exposes deep problems in self-reference and recursion. Can a game truly contain itself? If so, what prevents an infinite loop? Does the definition of a game break down when it allows infinite recursion? Are there limits to what we can call well-defined? This is similar to Russell's paradox in set theory, where a set that contains all sets leads to contradictions. Likewise, Hypergame seems to be both a finite game and an infinite one at the same time.
Even as a character, absolutely.
Welcome to level 74 of 100 paradoxes. Imagine you're watching a security camera feed showing a quiet street. Nothing is happening, so you look away for a few seconds. When you look back, you see that a car has appeared on the screen. Here's the question. Did the car appear while you weren't watching, or did it only exist once you looked again? This is the observer's dilemma, a paradox that plays with the nature of reality, time, and perception. It asks, does something exist when it isn't observed, or does observation itself create reality? At first, this seems like a simple issue. Of course, the car existed even when you weren't looking. But this paradox goes deeper. In quantum mechanics, the famous double-slit experiment shows that particles behave differently, depending on whether they are observed. When unmeasured, they act like waves, existing in multiple states at once. When observed, they collapse into a definite position. In philosophy, Berkeley's idealism suggests that reality only exists when it is perceived. If no one is looking at the moon, does it still exist? Or does the act of perceiving bring it into being? In theoretical physics, some interpretations of reality suggest that time and space themselves may not exist independently of observation. The universe might only take on a definite form when measured. This paradox raises unsettling questions. If something isn't observed, can we ever be sure it exists? If observation affects reality, does that mean the world is shaped by our awareness? Does time itself move forward when unobserved, or is it just an illusion created by the act of looking? Some physicists suggest that the universe might function like a giant quantum system, only solidifying into a definite state when measured. Others argue that reality is always there, but we only experience a fraction of what truly exists. The observer's dilemma forces us to ask, is the world around us truly independent, or do we play a larger role in shaping reality than we realize? Welcome to level 75 of 100 Paradox. Imagine a machine that can erase specific memories from your mind, leaving everything else untouched. You decide to erase the memory of using the machine itself. Now, here's the paradox. If you don't remember using the machine, did you ever actually make the decision to erase your memory? This is the memory erasure paradox, a thought experiment that challenges the nature of free will, identity, and
But it's like they don't wake up
At
until they're
first,
like super,
it seems
super
simple.
old. So it's just like
You
take
make the
care
choice,
It's
erase
got,
the
like,
memory,
when they're
and you
old.
don't. But if you no longer remember making the choice, then from your perspective, the event never happened.
All that. Back
One,
did
did you truly decide, or was the decision erased from history? Two, if you later question why you feel like something is missing, would you think you were ever given a choice at all? Three, what if someone else erased your memory? Would you ever know you had lost something? This paradox touches on deep philosophical and psychological problems. One, the illusion of choice. If your memory of making a decision is erased, can you still claim you have made that decision? Two, the ship of Theseus problem applied to the mind. If parts of your memory are removed, at what point do you become a different person? Three, self-referential. What happens if you keep erasing the memory of erasing your memory? Would you ever truly be able to track reality? Some argue that identity is tied to continuous memory. If memories define who you are, then erasing even one event means the version of you that made that decision no longer exists. Others suggest that the conscious mind works in real time, so even if the past is erased, it doesn't matter because the present self is still real. The memory erasure paradox forces us to ask, if you forget a decision, did you ever really make it? And if your memories define you, what happens when parts of your past are erased forever? Welcome to level 76 of 100 Paradoxes. Imagine you flip a coin, but before you see the result, you take a pill that erases your memory of flipping it. A friend sees the result and tells you afterward, you flipped the coin, but you don't remember it. What do you think the outcome was? Logically, the coin still landed on heads or tails, just like any normal flip. But from your perspective, you have no evidence that the coin flip even happened at all. Now, here's the paradox. If you assume the flip happened, the probability should be 50-50, heads or tails. But if you have no memory of flipping the coin, do you have any reason to believe the event happened at all? If you repeat this experiment multiple times, and each time your memory is erased, can you ever be sure that any flips occurred? This paradox combines ideas from probability, memory, and perception. Probability without evidence. If you have no memory of an event, should you still assign it the same probability as if you remembered it? Self-consistency in time. If the past leaves no...
Phillips Oracle Window presents Shade of All Things. Your sound made simple. Phillips Oracle Window 360. It's Friday. How'd they get to work? From the director of the Transfer and Suicide Squad. After slapping that woman that room with my wife. For slapping a wife. I'm looking at rated R. Indians Friday.
We drilled a little too deep.
Thanks, Rose. I see it.
Leaves no impact on your mind. Does it still exist for you? Infinite regress of forgotten events. If every time you flipped a coin, your memory was erased, would you ever be able to confirm that a single coin flip happened? This paradox is similar to Sleeping Beauty, but with a crucial difference. Instead of questioning probabilities based on repeated awakenings, it questions whether forgotten events can even be meaningfully assigned probabilities at all. Some philosophers argue that the past is real, regardless of memory. Just because you forget something doesn't mean it didn't happen. Others suggest that personal experience is what defines reality. So if you don't remember flipping the coin, it may as well have never happened to you. The forgotten coin flip paradox forces us to ask, if an event leaves no trace in your memory, can it still be considered real? And if all your past decisions were erased, would you still be the same person? Welcome to level 77 of 100 paradoxes. Mathematics is supposed to be precise, logical, and free from contradictions. But what if infinity itself refuses to behave the way we expect? This is Stalin's paradox, the mind-bending problem in set theory that challenges how we understand numbers, size, and even reality itself. In mathematics, there is a concept called countable infinity. This is the kind of infinity that includes all the natural numbers. 1, 2, 3, 4, and so on, forever. Even though this set is infinite, we can still list the numbers one by one. Then there is uncountable infinity, which is even larger. The real numbers, like pi, e, and irrational numbers, form an uncountable set, meaning there are more real numbers than there are natural numbers, even though both sets are infinite. Mathematician Georg Cantor proved this by showing that no matter how you try to list real numbers, there will always be some missing. So far, so good. But here's where Stalin's paradox comes in. In formal logic, we can describe the set of real numbers using mathematical rules. However, a theorem called the Loewenheim-Skolem theorem says that if a mathematical system has an infinite model, then it must also have a countable model, one where everything still works logically, but the uncountable real numbers somehow behave as if they are countable. This leads to a paradox. 1. The real numbers are uncountable. This is the fundamental mathematical fact. 2. But Skolem's theorem says that in some logical models, the real numbers can appear countable. 3. How can something be both countable and uncountable at the same time? This seems absurd. If a mathematical structure proves that uncountable numbers exist, how can we also create a logical system where those same numbers appear countable? Some mathematicians argue that this paradox isn't really a contradiction, but instead shows that formal mathematical descriptions can be tricky. Just because a model behaves a certain way inside its own logic doesn't mean it reflects the true nature of reality. Others suggest that it exposes deeper limits in how we define mathematical objects, questioning whether infinity itself is as rigid as we assume. Skolem's paradox forces us to ask, if math itself can describe an uncountable set as countable, how much of what we believe about numbers is just a result of the system we use? Welcome to level 78 of 100 paradoxes. Imagine standing in front of a bright light, casting a shadow on the wall. Now, imagine moving the light farther away. Your shadow gets bigger and stretches out, but it remains sharp and well-defined. Now, here's where the paradox begins. What if the light source were infinitely far away? Would your shadow become infinitely large? If so, does that mean your shadow is now covering the entire universe? At first, this might seem like a simple question about physics, but it reveals a deep paradox about infinity, perception, and existence. Shadows are cast when light is blocked by an object. If a light source is extremely far away, the shadow grows and spreads. But in an infinite universe, this leads to strange contradictions. If your shadow becomes infinitely large, does that mean it exists everywhere at once? Can something infinitely large still be called a shadow? Or has it become something else entirely? If light is needed for shadows, but light is infinitely distant, does the shadow even exist at all? This paradox isn't just a trick of the imagination, it ties into real questions in physics and philosophy. 1. The horizon problem in cosmology. If light takes time to travel, can any part of the universe truly see another part? 2. The nature of information spread. If a shadow grows infinitely, does it carry information forever, or does it fade into meaninglessness? 3. The concept of infinity in reality. If something stretches infinitely, is it still real in any meaningful sense? Some physicists argue that an infinitely large shadow doesn't make sense because shadows rely on contrasts. If everything is covered, is there really a shadow at all? Others suggest that infinity itself is an illusion, meaning that even though mathematics allows for infinitely large things, reality does not. The infinite shadow paradox forces us to ask, if something stretches across infinity, does it still exist as a single object, or does it dissolve into nothingness? And if a shadow can cover the entire universe, does that mean it is no longer a shadow at all? Welcome to level 79 of 100 paradoxes. Imagine you are given a 100% accurate prophecy of your future. The prophecy tells you exactly what will happen tomorrow, down to the smallest detail. But there's a catch. As soon as you read the prophecy, you will forget it. Now, here's the paradox. The future is predetermined since the prophecy is always right. But you don't remember the prophecy, so you make decisions as if you don't know the future. If you don't know the future, are you still following a predetermined path, or are you acting freely? This is the forgotten future paradox, a thought experiment that challenges the relationship between determinism, free will, and memory. At first, it seems like free will still exists. Since you don't remember the prophecy, you experience choice as if you are making your own decisions. But since the prophecy is never wrong, that means every decision you make must align with it. Are you truly choosing, or just acting out a script? If forgetting the future still leads you to the same outcome, does knowing it even matter? Does memory determine free will? Or does it only create the illusion of control? This paradox connects to deep questions in physics, psychology, and philosophy, quantum mechanics, and the block universe. If time is just another dimension, does that mean our future is already set, and we are just experiencing it step by step? Neuroscience of memory and identity. If you forget an event, does that mean it never affected you? How much of free will depends on remembering our choices? Predestination versus free will. If everything is already written but we can't remember it, does that mean we are both free and bound at the same time? Some argue that free will is an illusion, and whether or not we remember a choice, it was always going to happen. Others suggest that memory itself is what makes decisions feel real, meaning without it, our choices might not even exist. The forgotten future paradox forces us to ask, if the future is set, but we don't remember it, are we still making choices? And if forgetting changes nothing, does knowing the future actually matter? Welcome to level 80 of 100 paradoxes. Omnipresence is the idea of being everywhere at once, an all-encompassing presence that exists in all places, at all times, without limits. It sounds like the ultimate power, but when examined closely, it leads to contradictions that challenge whether it is even possible. If something is truly everywhere, does that mean it occupies every space, no matter how small? Can it fit inside the tiniest possible area, or is it stretched infinitely thin? If it exists in all locations at once, is there any meaningful difference between one place and another? And if it takes up all space, where does that leave everything else? This leads to a strange contradiction. If omnipresence means fully existing in every possible place, then it must exist in paradoxical locations. Inside a black hole where physics breaks down, in a place with no space at all, like the quantum vacuum, or even in logically impossible locations, such as a shape with zero volume. Can something exist everywhere, even where existence itself is undefined? Then comes another problem. If a being is everywhere, does that mean it is everything? If it has no single location, can it have any distinct identity at all? If omnipresence means occupying all space, then how is it different from space itself? If it exists in all things, is it separate from them? Or is everything just a part of it? This also raises a question about free will. If an omnipresent being is in your mind, does it experience your thoughts as its own? If yes, then every thought, good or bad, belongs to it. But if no, then there must be some space where it does not exist, contradicting the idea of omnipresence. Some suggest that omnipresence doesn't mean being in all places in the same way. It could mean being able to access or interact with all places without physically occupying them. Others argue that omnipresence is a concept beyond human logic and isn't meant to be understood in spatial terms. The paradox of omnipresence forces us to ask, can something truly be everywhere without contradiction? Or does the very idea collapse under its own definition? Welcome to level 81 of 100 paradoxes. Imagine that technology has advanced to the point where immortality is possible, but with a catch. Instead of making your current body live forever, the process transfers your consciousness into a new body every time you are about to die. At first, this sounds like a perfect solution. Every time your body fails, you simply wake up in a fresh, healthy one. Your thoughts, memories, and personality all remain intact. You never die. But here's the paradox. Are you actually immortal, or are you just being replaced by a perfect copy each time? If the process works by copying your consciousness into a new body, does that mean the original you ceases to exist every time the transfer happens? If so, then every version of you only lives once, and the real you dies each time, meaning no single person is actually immortal. But if your consciousness is truly continuous, then what happens if a glitch in the system creates two copies at the same time? Now, both versions wake up believing they are the real you. Which one is actually you? If both have your memories and identity, did you just duplicate yourself, or did the process create a new person each time? This paradox exposes deep problems in how we define identity and continuity. If your consciousness can be copied, is there such a thing as a real you? If two copies exist at the same time, which one is the true continuation of your existence? Does the survival of your memories mean you are still alive? Or is the original version of you dying each time without realizing it? Some argue that identity is just a pattern. If your thoughts and memories persist, you are still you. Others say that consciousness is tied to a single, unbroken experience, meaning that if you are replaced by a copy, the original you is gone forever. The immortality transfer paradox forces us to ask, does immortality really mean never dying, or just being continuously replaced? And if every version of you thinks they are the real one, does it even matter? Welcome to level 82 of 100 paradoxes. Knowledge is supposed to be simple. If you believe something, if it is true, and if you have justification for believing it, then it seems like you know it. For centuries, this was the standard definition of knowledge, justified true belief. But in 1963, philosopher Edmund Gettier proposed a problem that shook this definition to its core. Imagine this. You're walking through a town filled with fake barns, hollow structures designed to look like real barns from the road. By chance, you look at the only real barn in the entire area and think, that's a barn. Your belief is true. It really is a barn. Your belief is justified. You saw it with your own eyes. But did you actually know it was a barn? Here's the problem. If you had looked at any other barn in the area, you would have been wrong. Your belief was true by accident, not because of any reliable reasoning. This is the Gettier problem. It proves that justified true belief is not enough for knowledge. Let's try another example. Suppose your friend owns a dog, and you believe they have a dog. But one day they secretly give their dog away, and immediately adopt an identical looking one. You still believe they have a dog. Your belief is true. They do own a dog. Your belief is justified. You see the dog all the time, but your belief was based on the wrong evidence. You thought they still had their original dog. So, did you ever really know they had a dog? Gettier's argument proves that knowledge requires something more than just belief, truth, and justification. But what? Some philosophers suggest we need an extra condition, such as requiring that knowledge must not be based on luck. Others believe that certainty is impossible, and we should redefine knowledge entirely. The Gettier problem forces us to ask, how can we ever be sure we truly know something? If knowledge can be justified, true, and still wrong, then what separates knowledge from lucky guesses? Welcome to level 83 of 100 paradoxes. Imagine waking up one morning with the strange feeling that you had a dream, but you can't remember anything about it. It's gone, vanished from your memory. Now, here's the paradox. If you can't remember the dream, did you ever actually have it? Dreams feel real when we experience them, but once they fade from memory, what proof do we have that they ever happened? If no trace of the dream remains in your mind, is there any difference between a forgotten dream and a dream that never happened at all? This is the paradox of the forgotten dream, a thought experiment that challenges how we define experience, memory, and reality itself. At first, it seems like the answer should be simple. If you had a dream, even if you forgot it, it still happened. But think about this. If an experience leaves no trace, did it ever really exist? If you never recall the dream, how is it different from a dream that never occurred? Is memory the only thing that makes an event real? This paradox has deep implications for consciousness and reality. If we expand this idea beyond dreams, it raises unsettling questions. What if we forget major moments in our lives? Do they still define us if we have no memory of them? If you were told that an event happened but had no recollection of it, how could you ever be certain it was real? If all of history were forgotten, would it still have happened in any meaningful way? Some philosophers argue that memory is what makes an experience real. If you can't recall it, it might as well have never happened. Others suggest that events don't depend on memory at all. They exist whether we remember them or not. The paradox of the forgotten dream forces us to ask, is reality defined by what we remember, or does it exist independently of our awareness? And if an experience disappears completely from memory, is it any different from one that never existed? Welcome to level 84 of 100 paradoxes. Probability seems like a straightforward concept. Events have chances of happening, and we can calculate those chances with the right information. But what if probability could change based on how we describe the same event? This is the Borel-Kolmogorov paradox, a problem of conditional probability that shows how our understanding of likelihood can shift depending on perspective. Imagine a sphere, like Earth, and randomly select a point on its surface. Now, let's calculate the probability that this point lies on the equator, given that we already know it's on some specific line of latitude. At first, this seems easy. If we assume a uniform probability distribution across the sphere, then every latitude line has an equal chance of being chosen. And since the equator is just one of many latitude lines, the probability of our selected point being on the equator should be zero, just like choosing an exact point from an infinite set. But now, let's describe the same problem differently. Instead of choosing a latitude first, imagine that we randomly pick a longitude, a vertical line running from the North Pole to the South Pole. Since every longitude line crosses the equator, and all longitudes are equally likely, the probability of landing on the equator suddenly seems to be 1 instead of 0. This is the paradox. The probability of the same event, choosing a point on the equator, changes depending on how we approach the question. The reason this happens is because of how probability distributions work on continuous spaces. Depending on whether we condition the probability by latitude or longitude, the outcome changes. This reveals a deeper issue. If probability depends on how we frame a question, is it truly objective? Can there be multiple correct probabilities for the same event? Does this mean probability is just a tool of description rather than an absolute truth? Some argue that paradoxes like this show the limits of probability theory when applied to infinite sets. Others suggest that probability isn't an intrinsic property of reality, but a way for us to model uncertainty based on how we define our conditions. The Borel-Kolmogorov paradox forces us to ask, is probability an absolute truth, or does it shift based on perspective? And if the same event can have different probabilities, what does that mean for how we understand chance itself? Welcome to level 85 of 100 paradoxes. Imagine a world where everyone is happy. The people in this world live fulfilling lives, experience joy, and have all their basic needs met. Now, imagine a second world where the population is much larger, but while everyone is still happy, their happiness is less intense. Their lives are just barely worth living. Which world is better? This is the mere addition paradox, a problem in ethics and population philosophy that challenges how we think about well-being, morality, and the value of life itself. At first, it seems obvious that the first world is better. Fewer people, but
life doesn't come with a builder's manual. Freedom is getting to so get 10% off a Jeep Wrangler or get you a Jeep Grand Cherokee. Your freedom is an on-road door where it's a front row seat to the city or a second row seat. And you're right. Life doesn't come with an owner's manual. You're just sitting down there like you are. Right now, during the Jeep Celebration event, one qualified current FCA listings use the 2025 Jeep Grand Cherokee the regular 4x4 for $259 a month. See your Tri-State Jeep Grand dealer today.
Ah, ponytail. The unofficial hairstyle of the morning rush. An official sign Caitlin means Cadet Kubrick. That's right, Caitlin. Hang out with him. Let your hair down. Or up. Up's good too. I actually like this.
But each one experiences a high level of happiness. But now, let's add a simple twist. Take the first world and add more people who have lives that are barely worth living, not suffering, but just above neutral. The total happiness in the world has increased because now more people are experiencing at least some joy. If we keep repeating this process, we eventually reach a world where a massive population exists, but each individual has a very low level of happiness. This leads to an unsettling conclusion called the repugnant conclusion, that a world with billions of people barely experiencing happiness would be considered morally better than a world with fewer people living extremely good lives. But is this really true? On one hand, total happiness has increased. So if we believe morality is about maximizing well-being, then adding more people, even if they are only slightly happy, seems like the right choice. On the other hand, this seems absurd. At some point, we might end up with an enormous population of people whose lives are just barely tolerable. Yet we are forced to call this better than a world where fewer people live truly great lives. This paradox challenges the way we define ethical decision-making. Is it better to have more people with lower happiness or fewer people with higher happiness? Does the total amount of happiness matter more than the quality of individual lives? If mere addition leads to a repugnant conclusion, does that mean our moral reasoning is false? Some philosophers argue that this paradox exposes the limits of utilitarianism, which focuses on maximizing happiness without considering individual well-being. Others suggest that quality of life matters more than total happiness, but struggle to explain why adding barely happy people is wrong. Welcome to level 86 of 100 paradoxes. Imagine you are standing in front of two doors, each leading to a different future. One leads to a life of happiness and success, the other to struggle and hardship. You must make a choice, but here's the twist. You are outside of time. Your decision has already been made in the future, but you haven't experienced making it yet. Now, here's the paradox. If the choice is already determined, do you still have free will? And if you are free to choose, how can the future already be set? This is the paradox of the timeless choice, a problem that challenges the nature of free will, determinism, and time itself. At first, it seems like a simple question. Either you have control over your choice, or the outcome is fixed. But what if both are true at the same time? If the future already contains your decision, then your choice is predetermined. But in the present, you still feel like you have the power to choose freely. How can both be true? This paradox connects to major ideas in physics and philosophy. 1. Block universe theory. Some scientists believe time is like a book. Every page already exists, meaning that the past, present, and future are all equally real. If that's true, then your choice is already written, even though you haven't reached that page yet. 2. Quantum mechanics. Some interpretations of quantum physics suggest that multiple futures exist, but the moment you observe them, it collapses into a single reality. 3. Fate versus free will. If your future is known, does that mean you're merely following a script? Or does your choice create the future in real time? Some philosophers argue that free will is an illusion. You only feel like you're making a choice, but in reality, it was always going to happen that way. Others believe that choices shape reality, meaning the future does not truly exist until the moment you decide. Welcome to level 87 of 100 paradoxes. Imagine you are watching a security camera feed of a locked, empty room. The screen shows nothing unusual, just an empty chair, a blank wall, and silence. But then, the feed cuts out for a single second. When it comes back, everything looks exactly the same. Now, here's the paradox. How do you know nothing changed while the feed was off? This is the observer vanishing paradox, a thought experiment that challenges how we define reality when we are not observing it. From your perspective, the room appears to be unchanged, but since you didn't witness that missing second, anything could have happened. A person could have entered and left. The chair could have disappeared and reappeared. Reality could have collapsed and restarted, leaving no trace. This paradox connects to deep ideas in physics, philosophy, and perception. 1. Quantum mechanics and the observer effect. In quantum physics, particles don't have definite properties until they are observed. Could the same apply to everyday reality? 2. The tree falling in a forest problem. If something happens where no one is watching, can we say it really happened? 3. Simulation theory. If reality behaves like a simulation, is it only rendered when observed? Could the missing second have been an error in how reality is processed? Some argue that reality is independent of observation, meaning the room remained unchanged whether or not you saw it. But others suggest that existence is tied to perception, meaning that for that missing second, the room had no definite state at all. The observer vanishing paradox forces us to ask, is reality always there, or does it only exist when we observe it? And if there are gaps in our awareness, can we ever truly know what happens when no one is watching? Welcome to level 88 of 100 paradoxes. Imagine a small, intelligent being, Maxwell's demon, who can cheat the laws of physics. He sits at the door between two chambers of gas, carefully opening and closing a tiny trapdoor. Every time he sees a fast-moving molecule, he lets it pass to one side. Every time he sees a slow-moving molecule, he keeps it on the other side. Over time, one side gets hotter and the other gets colder, creating a temperature difference without using any energy. This seems to violate the second law of thermodynamics, which says that entropy, disorder in a system, must always increase. But physicists later found a catch. Maxwell's demon doesn't just sort molecules, he must also store and process information about them. Now, let's add a new problem. What happens if the demon forgets? This is Maxwell's demon with information loss, a paradox that connects physics, computation, and entropy in a completely new way. If the demon keeps track of every molecule forever, he seems to cheat thermodynamics, but real systems can't store information perfectly. At some point, the demon's memory fills up, and he must erase old information to keep working. And here's the crucial twist. Erasing information creates entropy. In 1961, physicist Rolf Landauer discovered that whenever information is erased, heat is released, increasing disorder in the system. This means that no matter how perfectly Maxwell's demon sorts molecules, he must eventually delete old data, which restores entropy and prevents a perpetual motion machine. This paradox forces us to rethink not just physics, but also computation. If information is a physical thing, does memory storage itself obey thermodynamic laws? If forgetting increases entropy, does that mean every act of memory loss creates heat? Does this mean intelligence and computation are fundamentally linked to energy consumption? Some scientists argue that the universe itself may be like Maxwell's demon, constantly processing and erasing information. Others suggest that entropy is not just about disorder, it is directly tied to the limits of knowledge. Welcome to level 89 of 100 paradoxes. Imagine two scientists conducting an experiment in a high-tech lab. One scientist, Alice, stands inside an isolated chamber where an event will take place. A flash of light triggered by a quantum particle. The other scientist, Bob, stands outside the chamber, observing the results on a screen. Now, here's the setup. Inside the chamber, Alice sees the flash of light and records the time it happens. Outside the chamber, Bob's screen updates a few seconds later, confirming that the light flashed. But now, something strange happens. A glitch in the system erased Alice's memory of seeing the light. She checks her notes and finds no record of the flash happening. From her perspective, it never happened at all. Bob, however, still has the data on his screen, proving that the event occurred. Now, here's the paradox. Did the event actually happen if one observer has no record of it? And if reality is observer-dependent, which observer is correct? This is the observer-dependent causality paradox, a problem that challenges the very nature of cause and effect. At first, it seems like a simple mistake. Alice just forgot. But in quantum mechanics, an event's existence can depend on whether or not it was observed. If Alice has no record of seeing the light, then as far as she is concerned, it never happened. But Bob's observation says otherwise.